I just want to be the focus.
So,
Focus point.
welcome, how are you guys today? I'm glad you're here. I hope you guys are well. I hope this does nothing change that. It is Monday, or have to say in a very long time. So, I don't need all of this. This are quantum notes, but we're not there yet. So, it's a good thing we're not there yet because I haven't transferred it into my notebook yet. So,
Don't worry, when you get playing
So, I'm going to start by reminding you of Galilean relativity, which you probably haven't seen since very early in Physics 130. And I guess in the slightly out of order sense, this postulate applies across Einstein's special relativity and across Galilean relativity. So, so while I think this is probably postulate 1 for Einstein, it still holds true for Galileo. So, and it basically says that the laws of physics are the same. Fancy word for this is covariant. In any inertial reference frame. So, I kind of think of this as the guarantee that I'm not wasting your time, right? If the laws of physics that I was teaching you were only going to be true in this room, then you guys probably would ask for your money back. After hearing my dull droning monotone for at least one semester, I'm sure some of you want your money back anyway. But tough luck. We've already spent it. So that is effectively all postulate 1 is telling us, is that the laws of physics, if we really want to treat it as a law, it had better not just work in here. It had better work out there too. Yeah?
Yeah.
Okay. So let's start with the familiar, the comforting, the Galilean relativity that you guys have already grown accustomed to. And I'm going to cheat because I think Galilean is EAN, but I'm more sure that Galileo is LEO. So.
As long as you know how to spell it.
You know, this is one of those things where in the days before I recorded these things, I would just confidently misspell the word, and if someone said, that's not how it's spelled, I'd say, are you sure? But now I feel like I have to be more careful about how I spell things. So, it's not fair. Not fair to me.
Who's really watching these, Andre?
I don't even think Andre. I was looking at some of the view counts. There's a couple videos that have like 2 views.
Oh.
And I'm pretty sure I'm one of them because I check to make sure that that captioning is showing up.
Oh, yeah.
So.
Well.
Only 2 views. Are you sure?
Yeah. Yeah, Jeff and I were laughing about that a couple of weeks ago.
I know why. Because
It's also that bad in my Physics 130 course, though, so it's not just you guys. Clearly what that says is it's me, right?
Well, you have more students showing up in class, so there's that.
Okay, so I want to create, in honor of Galileo, two reference frames. An unprimed reference frame S and a primed reference frame S prime. And I want their axes to be parallel to one another. I just want the S prime reference frame to be moving at some constant velocity, which I'm going to put along the x prime axis. Yay? And so if you were to ask an observer sitting in a chair in frame S what S prime was doing, that observer would tell you that the observer in S prime is moving away with speed v in the x direction. Yay? An observer in S prime looking back at an observer in S would say that S is moving in the negative x prime direction with speed v. We're happy-ish.
Can you repeat again?
So this is just the Galilean approach, right? Although a lot of this is also going to apply when we jump forward a few hundred years. But I want to take one observer, and that observer is going to be sitting in a chair in the S frame, the unprimed frame.
Okay.
I normally put myself in the unprimed frame. I'm a creature of habit, and so that's normally mine, and I'm going to put you guys in the primed frame. But today, take your preference. I don't care. So an observer in the S frame, the unprimed frame, watching an observer in the primed frame is going to see that the observer in the primed frame is moving away in the plus x direction with speed v.
Okay.
An observer in the S prime frame, looking back at you sitting in the unprimed frame, is going to say that you have speed v in the negative x prime direction.
Yeah, yes.
So basically just, you just watching a car pass by?
Yeah, this is entirely such, right?
Yeah.
If you could actually imagine last week when you weren't stuck in this classroom listening to adult droning. Look at the people out there enjoying the sunshine as they walk, not in a rush, just casually, constant speed. Ooh, a bird, right? That could have been you, but no, you signed up for Physics 231.
Okay.
Those two frames, right? You're one of them, and they're the other.
Okay.
Is it the Robert Frost poem? Come to a road dividing. You took one path, and that made all the difference. So here you are. What I want is to make the argument that the two origins, O and O prime, coincided at t equals 0. So at t equals t prime equals 0, the origins coincided. Is that all right? Are we happy-ish?
What does coincided mean?
Coincident at the same location.
Oh, okay.
Hooray? So Galileo is then going to give you the following exchange rate between the measurements in one frame and measurements in the other. So we could say that here, let's here's a coordinate. Let's say that x prime, y prime, z prime is the coordinate according to this guy, and x, y, and z are the coordinates according to the unprimed frame. Yay? So Galileo is going to give you the following relationship between the two. X prime is just going to be x minus v times t. Yay? How far apart are these two origins at some time t?
V.
V times t. Yeah? So this distance, right, the unprimed x, is equal to v times t plus x prime. Yeah? Okay. So what about y prime?
Maybe the
It'll just be equal to y. It's not changing all that.
Yep. What about z prime?
Equal.
it would be the same thing.
Yep.
Why will they be equal?
Because what's the direction in which the two frames are moving relative to one another?
In the x.
In the x direction, right? So
So we only care about the axis.
well, you're only going to observe a change along the x or x prime axis, right? That's the only one they're going to disagree on. Does that work? What about t prime?
The same.
It's also t, right? We're happy-ish?
Wait, why we have so many x, y, z, and t? So we talk about dimension 4?
We are going to want to describe events. And the way that, I think I've even described this to you guys previously, but the way that I commonly describe this is there's only a couple ways onto and off of this campus, right?
I know.
So if you drive here, then your car was at the same location my car was at. I have yet to need to call my insurance company. Why?
Because the t.
Because the event is not just same location, it's same location at same time, right? The event that would necessitate me calling my insurance company. Yeah? Okay. So to describe events, not only do I need the 3 spatial coordinates, I also need the time coordinate.
Oh, okay.
Is that all right?
Yeah.
So if I wanted to describe velocities, how would I do so?
Velocity.
Yeah. So not only is this point just sitting here, let's say that this object is moving, and we both want to measure that velocity.
Take the derivative of the position.
Sure. With respect to time, right?
Respect to time, yeah.
And so we could argue that, well, since I already used v for the relative velocity between the two reference frames, I'm going to use u to represent a speed that we're measuring. Is that okay?
Okay.
So I'm going to say ux prime is u minus v. Yay? There's no magic in this? What if I wanted to know the speed of this thing in the y direction? Compare back and forth between the two observers.
The same?
Same. Right? dy prime dt prime is the same as dy dt because t prime is t. Oops. By same argument, I can say the same for z.
Yes.
We're happy-ish. Okay. If I wanted to find the acceleration of this thing, whatever it is we're observing, how do I get to that?
Take the prime of the speed.
Take the derivative yet once more. And so what do I get? Ax prime
With the respect
To
to
dx.
t, right?
just ax. Yeah? How can I get away with that? Taking the derivative with respect to t or t prime, right? This is a constant, yeah?
Yeah.
Yay? There's something heartwarming in this. So I'm told. I mean, I don't have a heart, but it warms the space where my heart's supposed to be. The two observers agree on acceleration, yeah? Tethered to this, though, is Newton's second, right? What does Newton's second tell me?
F equals ma.
F equals ma, right?
Yeah.
And so if we agree on the forces in the x, y, and z direction, what else do we agree on?
F is the same.
The net force that it was subjected to, right?
Yeah.
Okay, so again, this takes us back to this ability to not just talk about physics in this room, but for the happy people who are on the other side of that window, right? Conservation of happiness. The less happy you are, the happier they can be.
Is that a new law?
I'd like to coin that one, yeah. So far so good. You could also say that, Chris.
Wait, so v, like when you say x prime equals x minus vt, you're saying v is the velocity of the s frame.
The S prime frame as told by S. S prime would say S is moving in the negative x direction with speed v.
S prime would say the s frame is moving in the negative x direction.
Correct. So the locations of pluses or minuses would change if I wanted to write x in terms of something measured by x prime.
Okay.
Yay?
Yeah.
Hooray. Okay. Then notice that we get covariance of momentum. So let me try and fit this on one board. I know it's greedy given that there are many boards, but so let's say okay. That's not how you spell earlier. See, that's the confidence I used to effuse when
As long as the physics is right.
Well, I'll tell you, this isn't actually right. We're spending 25 minutes on something that we're gonna undo in a couple minutes. But it works very well at low speeds, right? This is, as you see me walking to my car later today and you want to throw
Eggs.
Eggs?
Eggs. Milky Way bombs.
as you're driving, right, and you're trying to calculate the speed with which it's going to hit me,
Yes.
Galilean relativity works just fine. It's only at significantly high speeds that we're going to need to start worrying about Einstein relativity.
Like space.
Okay. Momentum of object 1 earlier plus momentum of object 2. 2 earlier needs to equal momentum of object 1 later plus momentum of object 2 later. Yay, conservation of momentum. This is true in the absence of an external net force. But we just said that we agree on forces. Yay?
Yeah.
Then we could sub out ux1 prime earlier and ux2 prime earlier and their later values. In terms of ux's, we could say that I need more space than this. Whose idea was to put this all on one tiny little board? Yay? Not that that's at all legible, but yay, it's just swapping out these with this definition. That's all right or no?
It is.
Okay. But note that this is going to give me bless you.
Thank you.
I'm just going to say E instead of earlier. Yay. What nice thing happens here? Note there's a minus MV, minus MV. What can I do?
Cross them out.
There's a minus capital MV, minus capital MV. What can I do?
Cancel.
And so what we're left with is that MUX1 earlier plus capital MUX2 earlier equals MUX1 later plus MUX2 later, which is just the unprimed version of what we said at the start, right? Yay? We're happy-ish?
So what is the point we're trying to make?
I'm trying to show you that the first postulate holds for Galileo. That's all I'm trying to say right now. You would do this for an elastic collision conservation of kinetic energy. You'll see that it holds there too. I'm not going to do that because that involves squaring this term a couple times. I'm lazy. But you'll see that it works out just peachy. Yay? Okay. Then all is well and good for a long, long time. In fact, if you were taking this class, I don't know, 122 years ago, you think that's a long time. It's not. Someday, if you're lucky, you'll be old, and that won't seem that long. But
About a lifespan and a half.
yeah. I mean, you know someone from that era. So, if you were taking this class then, I would probably be telling you, the best and brightest of you, to not waste your time studying physics. Because Newton had solved all of physics a few hundred years ago. All that was left was the stamp collecting. No offense if anyone likes stamp collecting. The stuff that remained to be solved was, what is Newton's universal gravitational constant? Is it 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared? What is, the electric field constant? What is the magnetic field constant? We were done, right? Modulo, just figuring out the values of constants. That's not where we should be spending our best and brightest, right? So there were a couple of kind of annoying little problems. Sir?
This is an unrelated question. Do you know if there's like a pencil sharpener in one of these other rooms?
I don't think that there are pencil sharpeners in any of these rooms. In fact, I don't even think that there's a trash can in this room. We do have our lovely periodic table, though.
Yes.
So
I'm just asking because my mechanical pencil broke and it is.
I wish that I could help you out. All I can give you is one of these.
I've got a bunch of non-mechanical pencils still.
I apologize. I don't have a happy solution to that. So there were a couple of annoying little problems that didn't quite make sense, but as theorists are sometimes wont to do, they were blaming the experimentalists. One of these problems was the precession of Mercury's perihelion. Do you guys know what perihelion means?
No.
Peri?
Dodge.
Close. So helion, helios,
Dodging
Person or what?
sun,
Sun, yeah.
helios. So near the sun is, so planetary orbits, what's the shape of a planetary orbit?
Ellipse.
An ellipse. And so we say that this is grossly exaggerated. None of the planetary orbits are that elliptical, but perihelion is the closest point on the orbit. We say that the sun is at one of the foci. But perihelion is the closest past. Yeah? So it was known that Mercury's perihelion kind of slid around the sun. So that if you came back, rather than just mapping this over and over again, maybe the next time, again, not this exaggerated, but maybe the next time it did that. And then the next time it did that. That's getting way overboard, but yay? So that the perihelion goes like this, right? Does that make sense? So the precession of Mercury's perihelion was something that was known. You could observe this. We did observe this. The problem is Newtonian physics didn't have a ready answer for this. Try as we might to think, how could we get Newtonian physics to predict that? If physics really is just a set of models that's meant to help us explain the results of past experiments and predict the results of future experiments, how are we going to use Newtonian physics to make... We couldn't figure it out. That was a problem. It's Einstein who's going to get us there. Not with his special theory of relativity, with his general theory of relativity. Right? There were some issues that kind of should have been hints that physics wasn't as done as we thought it was at the time. And part of it is that we're going to have to walk away from this idea of Galilean relativity.
Professor?
Yeah.
Can I ask a question? Who was the scientist who said something like what you said, we pretty much discovered everything about physics? There was a scientist, wasn't it?
Lots of them around the late 1800s. It was an in vogue kind of idea. So I couldn't point to one, but it was not an uncommon belief.
Is it Lorentz?
I don't know if it would be Lorentz. Lorentz did a lot of work with Einstein to give us special relativity. So, all right. So I will try to figure that out for you as one of my assignments. So I do need to turn us back towards one of our discussions of light from I don't know how long ago. But I started talking with you guys about trying to measure the speed of light. And one of the people we talked about was Galileo, right? Do you guys remember Galileo's conclusion about the speed of light?
Too fast?
It was really fast, right? Fast enough that he wouldn't be able to measure it. That doesn't say whether or not it's finite or not. It just says that, you know, it was faster than he was capable of measuring. And then we got to PHYS231. PHYS231 gave us a decent measurement of the speed of light, right? This is one of the only moments where there's, I think, one more after this coming up, where I'm going to talk about Physics 230. And I recognize that not everyone has sat through Physics 230, but I'm really just going to talk about forces. So you could the electric force, you could think of it, however you want, right? It's just another force. The other thing I'm going to say about this is, and I apologize if you are planning on taking Physics 230 next, I'm going to spoil, not only will you have to listen to my dull droning monotone for 16 weeks, but kind of the big reveal at the end I'm going to ruin for you right now. J.C. Maxwell gave us Maxwell's equations. And Maxwell is able to derive the speed of light. I mean, that's pretty cool, right?
Yeah.
He gets to this point where, and the other cool thing about it is, not only can he derive the speed of light, it's equal to 1 over the square root of the electric field constant multiplied by the magnetic field constant. I mean, that's as simple can be, right? This was very good evidence that light was just a traveling disturbance of the electric and magnetic fields. It's an electromagnetic wave. It's all right? But I want to cite that in conjunction with this first postulate. The first postulate says that we are all going to agree on the laws of physics in inertial frames. Yeah? And so if Maxwell can derive the speed of light from the electric force law and the magnetic force law, then doesn't that mean that we should all agree on the speed of light?
Yes.
So, it does, but is our postulate right? That's the thing that remains for us. So, crowdfunding is, in some sense, a fairly new idea.
You starting a Patreon?
I don't even know what that is, so I'm going to say no, just in case it's something filthy, and then I'm...
No, it's
Okay.
help people design things.
Still no. But it's not that new an idea. Michelson and Morley. When I think crowdfunding, that's kind of what my go-to thought. First American to win the Nobel Prize in Physics, Michelson-Morley experiment. I think Morley was the American, or maybe he was the British, I don't know, one of them. They had kind of, so the other thing that isn't entirely new is helicopter parenting, right? Every generation mocks the next generation by, with those versions of when I was a kid, I had to walk uphill both ways through the snow. So this idea that parents don't let their children fail, yeah, that's how it's always been. I mean, my generation is just more obnoxious in the way that we phrase stuff. So, but it's to show you how not new it is. We even did this for light. So, Maxwell shows us great evidence that light is a wave, right? Electromagnetic EM wave, yeah? Hooray? The sound waves that you're hearing, they're traveling through a medium. What medium? They're traveling through air, right? Water waves have a medium. What medium do water waves travel through? Not a trick question. It's water. Yeah? Waves have a medium. If light's a wave, then we started to worry poor light needs a medium.
No, they don't need.
Well, but don't waves need media?
Light wave don't need.
Apparently, but that's with a modern eye, right? So we gave light a medium. We called it the ether. It had to have some pretty special properties, though, because we didn't add it to our repertoire until the 1800s. So, there were many precedent years where it must have been there, but we didn't notice it. So it had to be something that we couldn't see, what senses do people have?
Malleable.
Humans,
Smell,
see,
Touch.
touch, taste, hear, smell.
Yeah.
Okay, is that all of them?
Yeah.
Taste.
What amazing worlds you guys live in. So the ether had to be something we couldn't see, touch, taste, smell, or hear. Yay? It's there for light to travel through. Michelson and Morley had this kind of cool notion that the ether is just permeating the universe and light travels through it. So Michelson and Morley had this idea that Earth traveling around the sun, how fast does, you guys remember roughly how fast Earth travels around the sun to complete one lap per year?
30,000.
30,000 meters per second. Yeah. About 2.5 cities of San Francisco every second.
Shoot.
The Beta Breakers, third Sunday in May. Anyone running it with me?
No.
Nope.
Get up early on a Sunday morning.
Yeah, no.
I think it's like either right before or right after finals week.
No. Nope.
No?
If we skip the final,
I will be
we can do
working.
it.
I'll either be working or still in school.
So, Michelson Morley had this idea that as light traveled through so Alexis was talking about throwing eggs at me from a moving car. Bear in mind that this is from my perspective, not what you wish. Do I want the car driving towards me when he throws the eggs or driving away from me if he throws them as
Away
fast as
from
he can?
you.
Why?
Because
Because
you don't want
you are
you
simultaneously
don't want
moving
more
with it.
force on you. You want as little as.
The velocity the egg strikes me with will depend, right? It'll be more if he's driving towards me, less if he's driving away from me. Michelson and Morley had the same idea for light. So they built kind of this cool contraption. It doesn't really matter where you put the light, but do you guys know what a half mirror is? That's because you have all led wonderfully upright lives. When you watch a TV show and the police are looking through into the interrogation room.
You mean one-way mirrors?
Yeah.
Yeah.
So same basic idea. So
What half mirror? I don't understand. What half mirror? You mean half
One-way
for
mirrors.
size or half for what?
You can only see in one direction.
One
Oh,
mirror, one
really?
mirror is transparent, the other one is.
Like I don't know even this that kind of view. Why?
Kind of like tinted windows.
Okay,
someone
why?
has to. Hollywood keeps them in business, I think. So, so the basic idea is that you can compare two light beams and recombine them. We have a version of this in lab. I'll ask Jeff to set it up for you so that you can actually see what's going on. But and then they're interfering them, just like what you were doing up until last week, right? I can't draw this well enough, so I'll just have Jeff show you. But they did this with light traveling in one direction, and then they rotated the experiment by 90 degrees, like in a big vat of mineral oil, so that it was noise damped. Rotated it 90 degrees, and then did it immediately again. What they expected is that the Earth moving through the ether